Look at the buildings outside your window, the device in your hand, or even your own skin. Every physical object in your daily life began as microscopic dust, drifting through a freezing, invisible void. Space is rarely an empty vacuum. The galactic disk is permeated by giant molecular clouds, sprawling nurseries of hydrogen and helium that serve as the birthplaces of stars. 4.5 billion years ago, our entire solar system existed as a single cold fragment within a cloud much like the Orion Nebula. This fragment was already chemically enriched by the history of the galaxy. Previous generations of massive stars had lived and exploded, seeding the local gas with the carbon, oxygen, and iron required to build rocky planets. This nucleosynthetic pre-seeding meant the building blocks for biology were present before the first planet ever formed. Despite these materials, the cloud was trapped in a state of hydrostatic equilibrium. The inland pole of its own gravity was perfectly balanced by the outward thermal pressure of the cold gas. To begin the transition into a solar system, this balance required an external catalyst. That catalyst arrived as a massive shockwave. Evidence suggests a nearby supernova, or the intense winds of a Wolf-Rayet star, slammed into the pre-solar core, providing the energy needed to disrupt the equilibrium. This collision simultaneously crushed the gas and injected short-lived radioactive isotopes, like aluminum-26, into the cloud. We see the signatures of this injection today, locked within the decay products of the oldest solid objects in our meteoritic record. The compression pushed the local density beyond the Jeans limit, a threshold where gravity becomes the irresistible primary force. At this point, the cloud's internal pressure could no longer resist the collapse, and material began falling rapidly inward. Without this specific cosmic disturbance, the pre-solar core likely would have remained a frozen, inert mass of gas for billions of years. As gravity drove an inside-out collapse, material fell toward the center to build a dense, growing protostar. But the cloud possessed a slight spin inherited from the galaxy. This brings conservation of angular momentum into play. As the collapsing cloud's radius decreased, its rotational velocity increased. Like an ice skater pulling their arms inward, the system spun faster. This created a physical barrier. While material fell freely from the poles, centrifugal acceleration forced the equator material to flatten into a two-dimensional disk. This ancient physical mechanism is why the modern planets all orbit the sun on a nearly flat plane and in the same direction. We are living in the stabilized remains of that original disk. Gravity provided the mass, but angular momentum dictated the geometry, transforming a chaotic cloud into a structured, rotating environment. At the very center of the disk, mass continued to accumulate until the pressure and heat reached extreme levels. When the core reached 15 million degrees Celsius, the solar core hit a tipping point. The temperature was high enough to overcome the electrostatic repulsion of hydrogen protons, slamming them together and igniting nuclear fusion. The sun had officially become a main sequence star. This chart shows the temperature gradient created by that solar radiation. A distinct boundary, known as the frost line, separated the hot inner nebula from the freezing outer regions. Inside this line, the heat was too intense for water or methane to condense. Only rare materials with high melting points, like iron and silicates, could exist as solids. Because these rocky materials made up only a fraction of the nebula's mass, the inner planets remained small and dense. Outside the frost line, temperatures dropped low enough for volatile compounds to freeze into solid ice grains. This tripled the amount of available solid material, allowing for the rapid assembly of massive cores that could then capture vast amounts of hydrogen and helium gas. The difference between our rocky terrestrial neighbors and the outer gas giants is a direct byproduct of this ancient thermal divide. Planetary growth was a violent race. Microscopic dust grains stuck together to form early pebbles, and eventually planetesimals, which then began smashing into one another in a phase of runaway growth. Jupiter formed quickly, and according to the grand tack hypothesis, its interaction with the gas disk caused it to migrate aggressively inward. It acted like a gravitational snowplow, clearing out material as it moved towards the sun. This inward migration cleared the region where Mars was forming, stunting its growth, and compressed the remaining rocks into a dense ring between 0.7 and 1 astronomical unit. This concentrated ring provided the specific conditions needed to build Venus and Earth. Jupiter's inward journey was halted only when Saturn formed and migrated into a 2-3 gravitational resonance with it. This specific orbital configuration altered the balance of torques from the gas disk, which forced both planets to reverse course and migrate back toward the outer system. Had Saturn formed even a few million years later, the torque from the gas disk would have driven Jupiter into the inner system, consuming the material that eventually built Earth. Hundreds of millions of years later, the gas disk was gone, but the system was still undergoing a final reshuffling. The giant planets were still interacting with a massive belt of icy planetesimals at the edge of the solar system. The NICE model suggests that when Jupiter and Saturn reached a 1-2 resonance, it triggered a global instability. Uranus and Neptune were flung outward, crashing through the icy planetesimal disk and scattering bodies in every direction. This scattering event caused the late heavy bombardment, sending a storm of asteroids and comets raining down on the inner planets. We see the evidence of this era every night. Without an atmosphere to erode them, the moon's giant impact basins serve as a permanent record of this bombardment. Rock samples returned by Apollo astronauts confirm this timeline. These rocks were flash melted by massive impacts nearly 4 billion years ago, providing a definitive date for the collisions that shaped the inner system. This period of destruction served a specific biological purpose. When those icy bodies from the outer system slammed into a young, dry Earth, they delivered the massive reservoirs of water and organic molecules necessary for life. After 4.5 billion years, the solar system has reached a state of relative equilibrium. The violent collisions have largely ceased, and the orbits have stabilized. This history is written into our own biology. The iron in our blood and the carbon in our cells are literal pieces of the dead stars that seeded the initial cloud. As Carl Sagan observed, we are a way for the cosmos to know itself. Our current configuration is a record of specific physical events: the shockwave trigger, the momentum that flattened the disk, the gradient of the frost line, and the halting of Jupiter's migration. The modern solar system is the survivor of high-stakes physical lotteries. After 4.5 billion years of chaos, the orbits have stabilized, and we exist because this specific sequence of events